But let's say we have got a number of functions, phi1, phi2 up to phi n, okay, and we have already done it, okay, in the last class. So you've seen that if we are able to prove it this way, like c1 b, we can have the function in this form, phi1x, and c2 phi2x, then we have got cn phi nx is equal to 0. Okay. We can write down the function in this form, okay? And then we can actually prove whether this is independent or not. Okay, independent or not. In general way, we actually do it step by step. In the first step, we can just multiply it throughout, okay, and have an inner product of with phi1, so like this, plus c2 phi1 phi2 plus and so on. So we can write it this way, and cn phi1 phi n is equal to 0. Let's say this is the first one, and then what we can do is we can write down another equation where we have the inner product with, let's say, phi2. So maybe this is phi2 with phi1. Just keep a track of what we're doing here. Phi2 with phi2. So we are multiplying both sides by phi2. And we have got cn, and this is phi2 phi n. So in this way we can actually get up to nth row, okay, and this one we can actually have it as c1, and then phi n phi1 plus c2, this is phi n phi2, and then we can have it as cn phi n phi n. So it can actually take the form of a square matrix, and finally what we can have is something like this. We can have a matrix form phi1 phi1, and then we've got phi1 phi2, and then phi n phi1 phi n. Right. And the second one would be the second row of phi1, and then maybe phi2 phi2, and then we have got phi2 phi n, and then we can have the nth row, and nth row is phi n phi1 and phi n phi2, and we have got phi n. So whatever terms are there within this bracket, the inner product, these are all numbers. Okay? These are all numbers. So in general, if you're just taking it, okay, if you remember, we did it when we're talking about orthogonality, and these are all numbers. So finally, going to get a matrix of this form, okay, and if you can prove whether this is equal to 0 or not equal to 0, based on this, you can say whether it is an independent function or a dependent function, right? And this particular matrix form is written in terms of G. Okay, it's basically written in G, and this is called the Gramian matrix. Okay, so this is Gramian. So this is another way of showing whether a function, a set of function, is independent or dependent. Gramian determinant. Okay. So this is another method which can be used. Okay, I'm giving you an example right now. I'm just, since we talked about independent and dependent functions, you can just also use the Gramian method to do the same. Okay. So this is a way to do it, and that can be actually done. Okay. We also talked about orthogonality, and I think we can actually discuss this a bit, because we know We are going to do Fourier series in the next section. So we can actually maybe discuss this also. So let's consider three functions we have. Let's say 1, x, and x square. The question we you have to show whether they are orthogonal or not, and there is certain range within which it can be not. Depends on the function, of course. You have to show whether they are orthogonal or not. Okay, so is it orthogonal? So we have already seen if we have it in the matrix form, we can actually take the bracket function and then try to show whether it is 0 or not, so that we know that it is orthogonal or not. Okay, so we can have a function orthogonal, we can have a function as normal, then we can say that it is basically orthonormal in nature. Okay, so in general, when we want to show it, we have to know certain things. The first thing, these are the functions that we are talking about. The last slide, whatever I said, inner product, here it is. It is phi 1, phi 2, phi 3. Let's say these are representing your phi 1, phi 2, and phi 3. Okay, and this x1, x square, we have to show whether they are orthonormal or not within a range of, let's say, 1 and minus 1. And accordingly, we can do the checking. What we do is we actually take the inner product and we check for each of them. We take phi 1, phi 2, phi 2, phi 3, phi 1, phi 3. Okay, if all of them are more or less giving you the value is 0 with the inner product, then we can say that they are orthonormal. So let's take up phi 1 and phi 2. Okay, and we just do it mathematically. We actually take that multiplication and go from minus 1 to 1. And then the two products, two functions is 1, the other one is x. We take this dx here. Okay, do it. And then it's basically an odd function. So an odd function, and if you are integrating it with respect to minus 1 to 1, you should get 0. It's an odd function. So that's there. Let's straight away do it directly. No bit of mathematical tool that we use. And then we have got phi 2, phi 3. Let's see this. Again, minus 1 to 1. And then we have got x. And then we have got x square. And then we have got dx. So this is x cubed. So this is again one odd function, right? So if we just do the sum here, it will be minus 1 to 1. This should be again. Right? So fine with phi 1, phi 2, phi 2, phi 3. Let's take the third set. Phi 1, phi 3. And if we do it, it's minus 1 to 1. And then this would be 1 and then x squared. So this is not an odd function. This is an even function. If you take up for an even function, you are not going to get 0. So this would be x cubed divided by 3. This is minus 1 to 1 is equal to, and if we do it right, basically 1 by 3 is here, and this is 1, and then minus of 1, so it will be basically 3 side. This is 2. So this is 2 by 3, right? This is 2 by 3. This is not 0. So that means we can say that this is not orthogonal. If it was orthogonal, we can actually write down the normalized form of this. Not the orthogonal spelling. Orthogonal. Not orthogonal. Okay. So yeah, you can actually take up the inner product and check whether a function is orthogonal or not. Okay. In a similar way, we can actually take up one more problem. Here what we can do is not.
Hello, sir.
Yeah. Yes.
Sir,
Yeah.
sir, can you please repeat the first part of the uh, linearity dependent, independent, and then the
This one.
Yes, sir. At that time,
Okay.
my network was bad. That time, I could not hear you.
Okay, no problem. I'll repeat that. Okay. So see, let me just show from the second slide and then I'll go to the first slide. So you have, let's say three functions. Okay, we can consider them separate functions here. One, x, and x square. And if I want to take an inner product, I can easily do it. I can just take 1 and x and I can write it down, let's say 1 and phi 2. This will basically represent an inner product. Okay. So there is a way to show linearly dependent or independent, functions. And the technique that we can actually use actually called the Gramian method. The Gramian method. For that, we actually have to form a determinant, and basically we call it as the Gramian determinant. Now, how do you form it? We basically take the functions. You see, these are all separate functions. Okay, all these functions are linearly dependent or independent. For doing that, we are doing it. Okay? So what we do is, with each of these functions, we associate a constant c1, c2, cn, and then what we do is we take them separately. Let's say I'll just take up phi 1 and multiply with this. If I take phi 1 and multiply with this, I'm going to have a linear product between phi 1 and phi 2. 1 is there, it's outside. Phi 1 and phi 2 inner product, and then phi 1 and phi 2 inner product up to phi 1 phi n inner product. So these will be the elements or the components of the first row of the matrix that I'm going to form. In the second component, what I'm going to do is I'm going to multiply with phi 2. It will be phi 2 phi 1, phi 2 phi 2, and then phi 2 phi 1. That depends on how many functions you have. Just 3, that means
Sir,
there will be
what is
just 3
the
by 3.
inner product?
Yeah, inner product. Those are the inner product. What do you mean by inner product? If you just want to write down the form of inner product, you'll get something like this. Okay. So when you do the
Okay.
inner
How?
product, your voice is not clear, Sujita. Repeat.
Hello, sir. Here, how
Yeah.
you can choose the limit of the integration from -1 to +1?
Yeah. Yeah. So when you consider the function basically to be orthogonal, you cannot say that it is orthogonal for the entire range of minus infinity plus infinity. That might not always happen. So this will be predefined. It will be given that show that it's orthogonal within this range. Okay.
Oh, oh, okay, okay.
So that's important. Okay. So when you get a question on orthogonality, I'll probably also mention what is the range within which you have to check for orthogonality. Let's say it's a trigonometric function. Then most of the times the orthogonality will be between minus pi and plus pi, and you can check for the orthogonality. Okay. We'll see one more example. Okay. Then if you understand this property of inner product, we can actually use this property to show whether the Gramian is 0 or not. Okay. So here also, as I said, say if it's 3 function, it will be 3 by 3 matrix. 4 function, 4 by 4. So you're going to get a square matrix, no doubt. Okay. So it's a square matrix. Phi 1, phi 2, phi 1, phi 2, phi 2 up to phi n. Okay. So you're going to get a square matrix here. So you get a nth, inner product. Nth inner product will be multiplied with phi n, phi n phi 1, phi n phi 2, phi n phi n. So all these terms that are the inner product, this is all going to be pure number. Okay. So it's not that you are going to have 0 0. No, no, that's not the case. It's just a general case that I'm talking about. Yeah. So you might get a value like let's say 2 by 2. So you'll get pure numbers when you actually take up the inner product. So if you have a problem, I'm giving you something like this, and I'm talking about check the the linear dependency or independency depending based on the method. You have to do it in this way. Okay. Then what you can do, you can put it this way and see whether it is 0 or not. It is 0 or not 0, depending on that. In a similar way, we do it for determinant. We can comment whether it is dependent or independent, and that's the Gramian method. So because of this inner product thing, I have just done this example, and I've taken the help of this example to also explain what exactly we understand by orthogonality. Okay. So the question is orthogonal fine, whether it is orthonormal or not. Okay. So for showing orthonormal, also we're going to do another problem. So let me take one more problem now. Let's have a function, let's say 1 and comma cos x, okay, and maybe cos 2x. Okay. Then we can actually keep on going. Maybe we can have cos of x. We have got so many terms. Okay, let me say we have some more terms. So maybe cos of mx is any general term, and then this belongs, okay, to a range of, let's say, minus pi 2 plus pi. Yeah, that is important. So which is within what range you have to check the orthogonality or you have to check the orthonormality and so on. So in general, if I just want to let's say find out the orthogonal property, we can just take the inner product phi 1 and phi m. Phi m may be another any term, okay? All these are all cost terms, okay? So maybe this is phi 1, this is phi 2, this is phi 3, then we'll have somewhere phi n, maybe we'll have somewhere phi m and so on. Okay? Phi m is the general term that I'm saying. So I can just say this is this. And then I'm going to just do the integration minus pi 2 plus pi. Okay, and then I can pick up this to be 1, and then I will take it to cos. See, it's all 2, 3, 4, it's nx, so this can be written as cos nx dx. If we have that, we can just use the basic idea of integration. We can just say the sine of mx divided by m, and then we can just write it down to be minus pi 2 plus pi. So, sine of, already know it, m pi is equal to 0. And then you use the property, and then you finally find out that this is nothing but 0, right? So this is 0. So fine, we know it. We can take any other term, maybe we take phi n and phi m. M may be, 0 to infinity, so it may be anything. So this integration also, minus pi to plus pi cos of nx, then cos of mx and dx. And then I can actually, what I can do, I can expand it and take cos of ax plus cos of, so cos of x into cos of bx, I can really know. Take half of cos of a plus b, so we have m plus n into x plus cos of b minus b and minus n into x. And then you can take the dx of that. Okay, so so the results you kind of tend to remember it is important because in next unit we are going to do Fourier series, and Fourier series may is up to movie now and then. So the sine of m plus n into x divided by m plus n, and then maybe plus sine of m minus n into x divided by m minus n. This is equal to 0. This has to be equal to 0 because you see, if I take it from minus pi to plus pi, both of them are sine functions. You take it up, you get that answer is more or less 0. Okay, so if you take it with anything, okay, you take cos 2x, 3x, nx, nx, whatever, you are more or less going to get it to be 0, right? So in general, what we can say here is, so that means we can say therefore this comment is a set of orthogonal function. So we can take any term, we'll always see it will be 0. Okay. So this is actually simple. Okay. And before we proceed and check the orthonormality of the function, okay, maybe we can I'll give you a homework, you can try it. Okay. And here I'm going to tell you, let's say 1 sine x, sine 2x, sine nx, and so on. And this is also will be trigonometric function. I'll just keep it with minus pi and plus pi. Okay. So if to check whether it is orthogonal or not, okay, you can do it. Okay. So you can check these kind of problems. Might be something similar. Okay. So let's continue. Let's check normalization now. So what happens with normalization? It should basically give you the result. Okay, so it should be whether it is normal or not. Okay, let's check this. Let me just write down the general term. Phi m, phi n, okay, phi m, phi m. Okay. Let me just take phi m, phi m. So normalization means the inner product with itself. So I can take this, and this will be minus pi 2 pi. Okay, and if I just take the first function, let's say pi 1 was 1, if you remember, and this is dx. So this is x, pi minus pi, so this will be 2 pi. Right? If you do it, it is 2 pi. Right? So this is actually nothing but phi 1 square. Right? Because it's phi 1, so it will be phi 1 square. Okay? Phi 1 square get it to be 2 pi. And that is not normalized, right? So it should be 1, so it's not normalized. Okay, so we can see that phi 1 is equal to root over of pi. Okay, then we can take any other term. Let's try phi m maybe. Okay, and here maybe sorry m. Okay. So it will be minus pi to pi. Normalization is with the inner product with itself, right? And it should be 1, and then we can say it's a normal. So it's normalized. So it's not, then that means it's not normalized, and we have to make it normalized. So cos square m pi dx is equal to half, and we take an equation here, and then minus pi 2 plus pi. Okay, then this is 1 plus cos of 2mx. If we just expand it, okay, cos square mx cos 2x is equal to 1 minus 2 cos square x minus 1, right? And use that expansion. Dx half, we can take it this way, and then this is integration, this will be ux plus cos of 2mx would be sine of 2mx divided by 2m, and then we can integrate it from minus sign to pi. So this is half, not a problem here. And within the bracket, we can see is this is, this becomes 0, 2mx, okay, pi minus pi becomes 0. This is x, so it is pi minus the minus of pi, so it is 2 pi. So this is just pi. So whenever we are taking up all the other functions, you basically get phi m is equal to root pi, right? Because this is pi m square. So we have it, okay? Therefore, we can say, therefore, function is orthogonal, that is okay, no problem, but not normal. So we can write it that way. The function is orthogonal but not normal. And therefore, what we can do is, okay, you want to write down the normalized form, we have to just divide it by 1 by root over of 2 pi. Okay. And then we have cos of pi divided by root over of pi cos of 2 pi divided by root pi. So everywhere you have to just divide it by root pi. That's it. And then we have got cos of n pi divided by root pi. Now, if we actually check for normality, we'll see that this will become, the result is 1, inner product with itself, and then we can say that this is orthonormal. Okay, so now they are orthogonal or and normalized. So we'll just write down they are orthonormal. So if you actually want to convert a function and normalize it, we can actually do it in this way. Okay, so you have to just take care of this, that you understand this, because when we are doing Fourier series, we actually have to use these things some of time. So in general, if I can just write it down, we usually write it down in terms of the Kronecker delta. So if it is orthogonal, it's 0. If it is orthonormal, it's 1 with itself. Okay. So generalization, we can just say phi 1x, phi 2x. Okay. Up to, let's say, we limit to phi n x. Okay. And we say that it is orthonormal. Implies that this phi m and phi n is equal to delta mn, right? This is the inner product, right? And this will be equal to 0, okay, if m is not equal to n, and this will be equal to 1 if m is equal to n. Right? So this is the condition that you might have seen for a number of times. Then when we do a problem practically and write it down in form of vectors, not vectors, in a product, okay, we are going to prove it in this way. Now, why this is important? Because when we talk about Fourier series, we are going to have an expression, and we are going to write down the Fourier terms. Okay, as we do it, it will be more clear. But there we will see that if we have all the terms included, okay, they will basically be orthonormal in nature.